For the next few class meetings, we are going to be investigating the different power relationships in steady state sinusoidal circuits. We are going to start today by talking about the concepts of instantaneous power and average power. So let's first consider a simple system where we have a linear black box network like so. And we excite this linear black box network with a sinusoidal source. Does not particularly matter if it is a voltage source or a current source. And we measure some voltage V of t across our network's terminals. And we measure some current I of t flowing into our network. If our voltage V of t is of the form Vm cosine omega t plus some phase angle theta v, our current I of t is of the form Im cosine omega t plus theta I, then the instantaneous power as a function of time absorbed by our linear black box network is simply the product of our voltage and current. V of t multiplied by I of t. We are going to expand this relationship out to develop a specific equation. But in order to do so, I need to introduce a trig identity that allows this, or it tells us the rules for multiplying cosine functions together. Okay. So the trig identity that we are going to be using is this: cosine of x times cosine of y is equal to 1/2 multiplied by cosine x minus y plus cosine of x plus y, where in this case, x is going to be this angle and y is going to be this angle. So if we apply this trig identity, let's expand things out here. So we're going to have Vm cosine omega t plus theta v multiplied by Im cosine omega t plus theta I. If we apply our trig identity, this is going to look like 1/2 Vm Im cosine theta v minus theta I plus 1/2 Vm Im cosine twice omega t plus theta v plus theta I. Now I'm going to graph this function in a generic sense. So let's put P of T here, measured in watts. And then this axis is going to be our time, measured in seconds. And very generically, what we'll see, actually, I'm going to scooch this graph down very slightly. Is that we have a DC term that comes from this part right here. And I say that this is a DC term because Vm is a constant, Im is a constant, theta V and theta I are also constants. And so the cosine of the difference of those angles is a constant itself. So we just have a bunch of constants multiplied together. So it gives us some DC power. So I'm going to put the DC power level here. And then superimposed on top of that, we are going to have this AC contribution that actually has some time dependence. So arbitrarily just saying that theta V plus theta I looks like 0 degrees from the jump. This is going to look something like this. Where exactly half the time our AC power signal is above our DC offset, and exactly half of the time our AC level is below our DC offset. So we can actually call the DC contribution the average power, because half the time the power is above this value and exactly half of the time the power is below this value. And we'll more formally mathematically explain this here shortly. Okay. So the equation that we've developed, and I'm going to put a big box around it. And I'm also going to remember to write down AC right here. This equation is our generic equation for instantaneous power, in that it will work for anything. Doesn't matter if it's a source, resistor, capacitor, inductor, some combination of elements. This is a generic equation that works for literally anything, as long as we can express the voltage drop across the network and the current flowing through the network in terms of a phasor voltage and current, we are good to go. Okay. What we're going to do now is we're going to use this relationship and what we know about the behavior of resistors, capacitors, and inductors in steady state sinusoidal circuits to develop equations specifically for resistors, capacitors, and inductors. So recall that for a resistor, the magnitude of the voltage drop across a resistor, Vm, is given by Im, the magnitude of the current flowing through the resistor, times the resistor value itself. And recall that the phase angle for the voltage drop across the resistor has to be equal to the phase angle of the current flowing through the resistor. We developed both of these relationships when we're talking about our phasor rate relationships for circuit components. So under these constraints, our instantaneous power equation, P of T, can be written as 1/2 Vm squared divided by R, by simply substituting Im is equal to Vm over R times the cosine of theta V minus theta I. And since theta V and theta I are equal for resistors, we simply have the cosine of 0, which is 1. So we'll have 1/2 Vm squared over R times 1 plus, and now we have the other part. So this is going to be cosine twice omega t plus twice theta V. In this form, we're able to express the instantaneous power absorbed by a resistor only in terms of the voltage. So we only need to know the magnitude of the voltage across the resistor and the phase angle of the voltage across the resistor. We could just as easily express everything in terms of the current, which would look like 1/2 Im squared times R multiplied by a factor of 1 plus cosine twice omega t plus twice theta I. Our average power is simply the DC portion of our instantaneous power. So that would be 1/2 Vm squared over R, or 1/2 Im squared times R. For an inductor, the magnitude of the voltage Vm is equal to omega L times Im. And we know that the phase angle of the voltage is equal to the phase angle of the current plus 90 degrees. And if we substitute these relationships into our generic instantaneous power equation, let me put R here for resistor, we'll find that PL of T, the instantaneous power absorbed by an inductor, is going to look like 1/2 Vm squared over omega L. And then we have our cosine theta V minus theta I part. Well, theta V minus theta I is going to look like positive 90 degrees. Because we would have theta I plus 90 degrees, which is theta V, minus theta I. So theta I plus 90 minus theta I just looks like 90 degrees. Well, the cosine of 90 degrees is 0. So we don't have a DC contribution at all. Moving on to the AC portion, we're going to have 1/2 Vm squared over omega L, and then we'll have cosine twice omega t plus twice theta V minus 90 degrees, where our power is expressed only in terms of our voltage, and in terms of our current, we're going to have 1/2 omega L times Im squared cosine twice omega t plus twice theta I plus 90 degrees. Average power is simply 0. This is actually a pretty interesting result, because what it means is that in a steady state sinusoidal circuit, exactly half of the time an inductor is absorbing power, and exactly half of the time the inductor is supplying power back to the remainder of the circuit. We are going to see this show up again when we talk about complex power tomorrow. Lastly, for a capacitor, we know that the magnitude of our current, Im, is equal to omega c times Vm. And we know that the phase angle of our current, theta I, is equal to theta V plus 90 degrees. Using these relationships, we find that the instantaneous power absorbed by a capacitor is 1/2 omega c times Vm squared. When we do cosine of theta V minus theta I, this is going to look like cosine of negative 90 degrees, which is also 0. So we're going to move on to our AC term, where this is going to be cosine twice omega t plus twice theta V plus 90 degrees. And expressed in terms of our current, this is going to look like 1/2 Im squared over omega c times the cosine of twice omega t plus twice theta I minus 90 degrees. All right, so, and our average power here is also equal to 0. All right, so what I'm going to do now is I'm going to work an example problem. And we are going to try to figure out a couple of instantaneous and average powers, okay? So let's look at the following circuit. We're going to have a current source, Is of t, connected to a resistor. This will be a 15 ohm resistor. Up here, we will have a 5 ohm resistor. Here we have a 20 millihenry inductance, and connected in parallel to that 20 millihenry inductance will be an 80 ohm resistor. Let's say that Is of t is equal to 0.4 cosine (500t) amps. And our goal here is to determine 3 different things. The instantaneous power absorbed by the inductor, and just for the sake of argument, the average power absorbed by the inductor. The instantaneous power absorbed by the (5 ohm resistor, and the average power absorbed by the 5 ohm resistor, and then the instantaneous power supplied by our current source and the average power supplied by our current source. And I'm going to denote this specifically as supply. So let's talk about some things here. Our instantaneous power relationships are time domain quantities. However, we are going to do all of our circuit analysis in the frequency domain and then use those results to plug into our equations, okay? So for this problem, our first step has to be to convert our circuit from the time domain into the frequency domain. So I'm going to go ahead and work on that. This current is going to look like 0.4 angle 0 degrees amps in the frequency domain. Our 15 ohm resistor is going to remain a 15 ohm resistor. Our 5 ohm resistor remains a 5 ohm resistor. We're going to have to convert our inductor into an impedance, which I'll do in just a moment. And then we have our 80 ohm resistor, which is going to stay the 80 ohm resistor over here on the right. So here's a calculator. The impedance of our inductor is given by J times omega times L. In this case, omega is 500. So we have 500 times 20 times 10 to the minus 3, which looks like J 10 ohms. Now let's talk about some of the different things that we may need in order to solve for the powers that we're looking for, okay? So for our inductor in part A, if we know either this phasor voltage or this phasor current, we can solve for both the instantaneous power and the average power. For our 5 ohm resistor, if we know this voltage or this current, we can solve for the instantaneous and average power absorbed by our resistor. And lastly, for our current source, since we're trying to find the supplied power, we're going to have to know the voltage drop across the current source having this polarity. So, does anybody have any thoughts as to how we might solve for any of these quantities? All right, nobody is chiming in, so I will make a suggestion. I've got a couple of different thoughts on how we could potentially solve for some of these things, okay? So one thing that we could potentially do would be to perform a source transformation on the practical current source on the left-hand side of the circuit. In doing so, we could effectively use voltage division to figure out what V5 ohm is and VL is in a pretty straightforward fashion. And then we could add V5 ohms plus VL to find out what VCS is. So that's one route that we could go. Another route that we could potentially take here would be to use current division on the circuit as is, which would allow us to figure out what I5 ohm is. Effectively, we would lump the 5 ohm resistor, the J10 ohm inductor, and the 80 ohm resistor all into a single equivalent impedance and then apply current division, which would get us I5 ohms. And then we can apply current division again to the network as it stands once we know I5 ohms, which would allow us to calculate IL. And then we would wind up having to figure out V5 ohms plus VL in order to get VCS. Then there's always nodal analysis, which we would have to do a real full-on nodal analysis in order to find our voltages. There's also the possibility of doing mesh here to find all of our currents, but nodal or mesh would involve the use of a computer algebra solver. So did any of the 4 methods that I threw out there, any of them sound like something you would like to see? Source transformation. All righty. So I personally think the source transformation here is probably the easiest way to do it, but it's probably one of the least obvious ways to do it as well. So I am going to perform my source transformation down here. So I'm going to have a voltage source in series with my 15 ohm resistor. And the value of the voltage source is simply going to be 15 ohms times 0.4 angle 0 degrees, which looks like 6 angle 0 degrees volts. And now I'm simply going to connect the rest of my circuit. So here's my 5 ohm resistor. Here's my J10 ohm resistor. Here's my 80 ohm resistor. This is VL, which I am going to solve for here in a moment. This is V5 ohms, which I am going to solve for here in a moment. I'm not going to bother solving for I5 ohms, so I'm not writing it down. I'm not going to bother with solving for IL, so I'm not going to write it down. The reason I'm not writing VCS down is because VCS effectively no longer exists because we don't have a current source, okay? So once we know V5 ohms and VL, we could go back to our original frequency domain circuit and just employ Kirchhoff's voltage law around this loop. All right, so I'm going to use voltage division to find both of these voltages. Okay. So I'm going to start with V5 ohms. So that is going to be 6 angle 0 degrees volts multiplied by, I'm going to have 5 ohms in my numerator. And then I'm going to have 15 ohms plus 5 ohms. And over here on the right, I actually see 2 impedances in parallel. They both share the same voltage, so I'm going to have to put the equivalent impedance here. So that's going to look like J10 ohms times 80 ohms over 80 plus J10 ohms. And I'm going to throw this in my calculator, so please give me a moment. All right, so I'm getting a stack error, so I'm going to split this up into something easier for my calculator to figure out. All right, so what I got was 1.282 with an angle of negative 24.880 volts. Did anybody else get a similar result? So Sydney says she got that answer. Devarier says he got 1.162. So I'm just going to double check my math here. So 5 over 15 plus 5 is 20, plus J10 times 80 is 800I over 80 plus 10I. Then I multiply that by 6 angle 0. 1.282 angle negative 24.880. Yep, okay. So I feel pretty strongly that this is the correct answer for V5 ohms. For VL, actually, you know what? Let's hold on a minute here. Let's figure out what the power absorbed by the 5 ohm resistor is first before we move along here. So the power absorbed by the resistor, only knowing the voltage drop across the resistor, is given by 1/2 Vm squared over R times 1 plus the cosine of twice omega t plus twice theta v. So that's going to look like 1/2. Our voltage here is 1.282 volts squared divided by our resistor value. And we multiply this by 1 plus the cosine of twice omega. So it's going to be twice 500t plus twice negative 24.880 degrees. And I need one more close parentheses like so. And so let's see, 0.5 times 1.282 squared over 5 looks like 0.164 plus 0.164 cosine 1000t minus 49 point, let's see, 760 degrees watts. One thing that I do want to point out here, if I asked you guys to give me the instantaneous power at a very specific instant in time, which I absolutely ask of you in your in-class assignments, omega times T is expressed in radians, and this phase angle is expressed in degrees. So you would need to, when you put this in your calculator, either change your phase angle into into radians, or change omega multiplied by T from radians to degrees. And the conversion factor for doing that is 180 degrees is equal to pi radians. Okay, so if you were going to throw this in your calculator, you do need to make sure that your units for your angle is consistent here. All right. Now let's figure out what VL is. So using voltage division, just going to scroll up here so we can see it. So the voltage drop across our inductor is actually the voltage drop across the inductor in parallel with the 80 ohm resistor. So I'm going to have that in my numerator. So we're going to have, goodness, screen's getting away from me. 6 angle 0 degrees volts. J10 times 80 over 80 plus J10. And here we're going to have 15 plus 5 plus J10 times 80 over 80 plus J10 ohms. And give me just a moment, please. I'm going to throw this into my calculator. I get 2.544 with an angle of positive 57.995 degrees volts. From this, the instantaneous power absorbed by my inductor, my general equation, is 1/2 Vm squared over omega L multiplied by cosine of twice omega T plus twice theta V minus 90 degrees. And so now I'm going to substitute numbers in. So Vm for my inductor is 2.544 volts. Omega is 500. L was 20 millihenries. Then I'm going to have cosine of 2 times 500 plus twice theta V, 57.995 degrees, and then minus 90 degrees. And so this is going to look like 0.324 cosine 1000t plus 25.990 degrees watts. All right, let's see. We are going to be looking at our, or looking for the voltage drop across our current source now. So coming up here to this middle circuit, hopefully you all can see pretty much by inspection that the voltage drop across our current source is simply the voltage drop across our 5 ohm resistor plus the voltage drop across our inductor. So I can say that VCS is simply equal to V5 ohms plus VL. And because my memory is poor, I'm going to have to flip back and forth to remember what those voltages are exactly. So 1.282 angle negative 24.880. And then we have 2.544. Angle 57.995. Volts. Throw these into my calculator real quick. Typing too fast and missed a digit, so now I'm going to go back through and make sure I didn't miss anything else. Nope, doesn't look like it. So I get 2.987 with an angle of 32.792 degrees volts. Our instantaneous power for our current source is going to be 1/2 Vm Im cosine theta V minus theta I plus 1/2 Vm Im cosine twice omega t plus theta V plus theta I. And so if I put in my numbers, Vm in this case is 2.987 volts. Im is 0.4 amps from our problem statement. Cosine of negative 32.792 degrees, which is theta V, minus 0 degrees, which is theta I. And then I'm going to come over here and continue this. 1/2 2.987 volts times 0.4 amps times the cosine of 2 times 500 t plus 32.792. Apologies. Plus 0 degrees. And now I'm going to throw things into the calculator. Cosine of 32.792. I get 0.502 plus 0.597 cosine 1000t plus 32.792 degrees watts. So we found all of our instantaneous powers. Our average powers are simply the DC parts of all of our different bits, right? So the average power absorbed by the 5 ohm resistor is this bit right here. So here's P 5 ohms average. The average power absorbed by our inductor is 0 watts because there is no DC part listed here. And the average power absorbed by our current source is 0.502 watts. So this is PCS average. I know that this example problem was probably pretty boring, as most of this stuff is, because it's just rote math at this point. I wanted to do this because I've seen students kind of struggle to make the connection between analyzing in the frequency domain and using these equations in the time domain, in as much as I've seen them wind up with J's and angle operators and stuff like that in their instantaneous power equations, which should not be there. Your goal in working these problems is simply to figure out what the magnitude of the voltage or current is and the phase angle of the voltage or current is, and then plug those pieces of information into the equations that we developed at the beginning of class, okay? So it is literally do the frequency domain circuit analysis that we've been doing for the past week, and then take the results of that work and throw them into these equations that we've developed here at the beginning of class. All right. This next bit is, I guess, kind of optional. I think there might be a homework problem or two that is associated with it, and it's going to serve as a little bit of a lead in to what we're going to be doing in class tomorrow. So we determined the average power of our signals effectively by inspection and understanding what it means when you have a sinusoidal signal. We are going to do something a little bit more mathematically rigorous here and wind up getting the exact same result. Okay. So let's start by introducing how we can determine what the average value of a function is. So let's say that x of t is a periodic function. Does not matter what type of function it is at all, just that it is a periodic function. So it could be a sinusoid, could be a square wave, could be anything we want, as long as it repeats itself at regular intervals. The average value of our function x of t, we will call x average, is given by the integral of x of t dt, where we have to be very specific about our limits of integration here. I'm going to list this as negative t, or negative capital T over 2 to positive capital T over 2. Really what's important here, though, is that we are integrating over exactly one period of the function. So this could be, it's literally the exact same thing as integrating from 0 to capital T. Does not matter as long as we integrate over exactly one period. And we integrate over one period, and then we divide by the duration of the period. So this is our generic equation for determining the average value of a periodic function. For our power equation, this is going to look like 1 over the period. We'll talk about what that is in a moment, times the integral over 1 period of 1/2 Vm Im cosine theta v minus theta I plus 1/2 Vm Im cosine twice omega t plus theta v plus theta I. I'll close this off, integrate with respect to time. I'm going to go back a few pages here and just steal that graph that I drew. Because all we're trying to do right here is figure out what our limits of integration are going to be, or at least understanding it, okay? So this is my graph. And I'm going to use this green line right here to identify one period of this sinusoidal waveform. All right. So we have a periodic function. But what we've done here in our math is we've split the periodic function into the sum of two things. So it's that that horizontal line at P average, and then on top of that, we have the AC term. So we're just adding that AC term on top of that DC value. Well, in our integration here specifically, or we're going to break this integral up into two parts. Okay, so let's start with that. So we could say that our average power, P average, is 1 over our period T times the integral from 0 to T of 1/2 Vm Im cosine theta v minus theta I dt plus the integral from 0 to T of 1/2 Vm Im cosine twice omega t plus plus theta v plus theta I, using the generic form. dt, and close my brackets. Well, what happens when I integrate a sinusoid over one period? So if I'm looking only at the AC part of this power, because I've split my integral up, I'm just dealing with this bit. Okay. There, if I can draw correctly, the area above the horizontal line is exactly canceled out by the area below the horizontal line if I integrate over an integer number of periods. So if I'm only doing my integration from here to here, what's the area under the curve? It has to be 0. So this whole term goes away. And I'm left with just the DC portion. Well, 1/2 Vm Im cosine theta V minus theta I is a constant. So I have 1/t times 1/2 Vm Im cosine theta V minus theta I multiplied by the integral from 0 to capital T dt. So this just looks like capital T over T times 1/2 Vm Im cosine theta V minus theta I. These guys cancel each other out, and we're left with an average power of 1/2 Vm Im cosine theta V minus theta I. So mathematically, we get the exact same result as we got just by looking at our graph, or the graphical representation of our power, and figuring out, well, half the time it's above this level, half the time it's below this level, so that level in question has to be our average power. All right, that's enough of me harassing you guys with math for the day. If you have any questions, I would be happy to answer them. If not, I will see you tomorrow afternoon, where we are going to talk about effective values and then introduce the concept of complex power.